case of thermodynamics. So we had told that energy can be treated in two different ways. Energy in transit, that means whenever you will observe that the energy is crossing the boundary of the system. So if you find a system is interacting with another system, then if the energies are crossing the boundary, then you can refer to as energy in transit. This type of energies obviously will be path function, work, and heat transfer are the examples of this energy in transit. And also we discussed that energy can be also in a storage form. Internal energy or intermolecular energy are the examples of this kind of energy. So regarding the work transfer, regarding the energy in transit form, we mentioned that PDV or displacement work is the fundamental kind of work which we need to understand very minutely. So we had continued our discussion regarding this PDV or displacement work. We had calculated the PDV work for different thermodynamic processes available. Now, today I would like to tell you that except PDV or displacement work, there are a lot of different kind of work transfer available. You must remember that whenever we are referring to the single word work transfer, it refers to mechanical work transfer. Okay, except mechanical work transfer, there are lots of different forms of work transfer available. So they are in regular practice, like electrical work, like work done due to stretching of a work, like shaft work, like flow work, like paddle wheel or stirring work. So these kinds of work we will need to study. So we'll continue our discussion and we'll discuss these different forms of work available in practice, starting with the electrical kind of work. So let us start regarding the discussion of electrical work. So whenever there is current flow into a resistor, the resistor is our system here. Okay, so whenever there is current flow through a resistor, there is work transfer into the system. So now our primary concern is to calculate the amount of work done. We need to calculate the magnitude of the work done. So regarding that, we need to assume some basic or fundamental informations, like we shall assume that DC amount of charge has been flown through the electrical uh, circuit in a certain time period dt. Okay, so DC amount of charge has flown through the electrical resistor in dt time. Now from the concept of electrostatics, we can easily understand this I, or the electricity which is flowing through the resistor, is nothing but the DC dt. Okay, so now we need to move on to calculate the work done. So this work done, let us take dw as an infinite small work done. So this dw will be a function of the voltage difference which is maintained through the resistor, and the charge. So from this equation, dc can be written as I into dt. So rewriting here, we get dw equal to vi dt. Now if we want to calculate the total work done, then w will be, we need to just integrate this equation over a certain time interval. So let us take that time interval 0 to t. So it will be w is the integration of vi dt. Now if you want to calculate the rate of work done, we need to know how much work has been transferred to the resistor for a certain time. So our motive is to calculate the work done per unit time. So that is nothing but the electrical power which we are concerned of. So let us consider electrical power as P. So this P, so now from the basic concept of calculus, we know that this dt should be very close to 0. So limit dt tends to 0, it will be dw, that means work done per unit time. So calculating this will yield a very simple result, that is v dot I. So which is already given here, we dot is equal to vi. So work done per unit time, or specifically to say electrical work done per unit time, is nothing but V into I, that is voltage into electricity. So regarding this discussion, we shall move on to a problem where these concepts will be dealt in a much more better way. We shall see that a conjugate problem has been arranged, how this electrical work can help to move a piston, or how it can help to stir a certain amount of fluid. So we will see a conjugate problem, and thereafter we shall understand the concept of electrical work in a much better way. So let us move on to that. So if you just read the problem here, you can see that there is an electrical motor which drives a stirrer filled with a horizontal cylinder. The dimensions of the cylinder are given here. The cylinder contains a fluid which is restrained by a frictionless piston. That means the pressure which is applied by the fluid is balanced by the weight which is given on the piston. Now what happens? The fluid is being stirred for 15 minutes. Now what happens? The temperature of the fluid, because of this stirring action, obviously increases. Then the fluid inside this container or this cylinder obviously tries to expand, and for this expansion process the piston moves outward slowly by a distance of 30 cm against the atmosphere. So the atmospheric pressure is 1 bar, which is given to you. The current which was supplied to the motor is given as 0.5 ampere. So current is equal to 0.5 ampere. The voltage of the accumulator was given as 24 volts. Now the conversion efficiency from electrical work to mechanical work is 90%. So what does it mean? So just refer to the first line. An electric motor drives a stirrer filled with a horizontal cylinder. What does it mean? That means the energy which is being generated by the electrical motor, that is being supplied to the stirrer to create the stirring motion. So that means electrical work is transferred to the stirrer. Now regarding this transformation, regarding this conversion, some amount of energy is wasted. So 10% energy is wasted. So if 100 joules is produced by electrical work, then 90 joules will be supplied to the stirrer. So now our question is that we need to calculate the work done on the motor, stirrer, and the atmosphere and the atmosphere. So let us start with the work done on motor. So we had just discussed the formula of work done on a system by the help of electrical energy. That means we had discussed about electrical work transfer. So let us write we as the work done on the motor. So it should be simply written as V into I into dt. dt refers to the time period. So voltage is 24 volts, current is 0.5, and the time is 15 minutes. So we need to convert this 15 minutes into seconds. That is very simple. So ultimately it will give a result of 10.8 kilojoule. So using the simple formula of electrical work transfer, we can calculate the work done on the motor. Now we have just discussed that 90% of this work done is transmitted to the starter. That means if 10.8 kilojoule is the amount of work done on the motor, then the work done on the starter will be 90% of 10.8. That means 0.9 into 10.8. That will give us the value of 9.72 kilojoule. That is very simple. Now we need to calculate the work done on the atmosphere. Now who is doing the work on atmosphere? The fluid which is stored inside the cylinder gets the thermal energy of the fluid gets increased because of the stirring action. So because of the stirring action, the temperature of the fluid is increased, and the thermal energy which was contained, it also gets increased. The increase in thermal energy helps the piston to expand a certain distance of 30 centimeter against the atmospheric pressure of 1 bar. Then if we want to know the work done on atmosphere, then we shall use a simple formula, that is force. So force is nothing but pressure into area, and force into displacement always refers to the work done. So this is force and this is the displacement. So what is the force? What is the pressure? It is 1 bar. Then it will be 1 into 10 to the power 5. So we are trying to refer this pressure in kilopascals. Okay, so that ultimately we can calculate the work in kilojoules. It will be the area of cylinder. Now you can see the diameter of the cylinder is given as 40 centimeter, so it will be pi by 4. So we need to know that this diameter should be converted into meter. So similarly, the displacement also needs to be converted into meter. So it becomes 0.3, and ultimately the result becomes 3.77 kilojoule. That means this is the stirring work. So this was the input energy to the fluid, and so 9.72 kilojoule was provided to the fluid, and from this 9.72 kilojoule, 3.77 kilojoule is used by the fluid to cause a certain expansion of the piston by a distance of 30 centimeter. I hope that you have understood. So energy is being transferred from motor to the stirrer and stirrer to the fluid. Okay. So this is a very simple problem. You just need to understand the concepts. So I hope that you have understood the problem very minutely. So there was nothing special application of electrical work transfer, but still there was a basic formula which was required. So after the discussion on electrical work, we have moved on to paddle wheel work or stirring work. So here we can see a system present over here which contains a certain amount of water. So this is obviously a closed system with some adiabatic walls. That means no heat can penetrate through this wall. So no heat transfer takes place. Okay, from the so no heat transfer from the surroundings takes place. Now what happens? A stirrer or a paddle wheel is being inserted into this water, and this stirrer is connected with a weight. Now what happens? This If this weight is lowered down, it will cause a certain motion of this stirrer. The stirrer will start to rotate. So if the stirrer rotates, the 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 temperature of the water will obviously increase. Since the volume of this water is obviously constant, the volume is not going to change. We can specifically mention that there is no chance of PDV war. So this PDV war is obviously zero. Now, if we want to calculate the work done because of this stirring action, then we need to know the mass of this weight. Let us consider the mass is m, which is we are assuming that this mass has been lowered through a distance of dz. That means this weight, the weight which had mass of m, is lowered through a distance of dz. Okay, and t amount of torque is being transmitted through the shaft to rotate this paddle wheel. Now we need to calculate the work done by this stirring action. Now, when the shaft is transmitting the torque, let us the angle of transmission be d theta. So, the angle in which T torque is being transmitted is d theta. Now, we need to calculate the work transfer into the system. So, from simple concept, from the simple concept of work, we can easily say that this dw, so as there is a simple change of potential in it, so you can easily write mg dz. So this mg dz comes from the change in potential energy. So dz was the distance by which the weight was lowered. So this is the change in potential energy, which in turn generates this work, and this can be also written as t d theta. So this W can be written as mg dz, as well as it can be written as t d theta, because of the uh, torque T and the angle of transmission d theta. Obviously, you can say that this dw will be equal to t d theta. Now we need to calculate. If you wish to calculate the whole work done, then we have to integrate it over a certain interval. So we'll write w is equal to the limits. So let us just write me much more clearly. So let us take the limits 1 to 2. So 1 refers to the initial condition of the variable considered here, and 2 refers to the final condition. So mg dz, or we can write this same in a same format, it will be t d theta. So the conceptual thing is that since the volume of the water doesn't change, the volume of the water remains constant, there is no PDV work or displacement work involved here. Still there is work transfer into the system, and you have to remember that this is work transfer into the system. That means because of the surroundings, some work is generated into the system. Okay, so I hope that it was understandable to you. So you just need to remember the formula. So this is nothing but the change in potential energy, that is mg dz, and you can also calculate the same from the perspective of torque and the angle of transmission. So after the discussion on parallel work or studying work, let us take a problem and solve it so that we can understand the concept of parallel work or studying work much more efficiently. Let us read the problem. So a piston and cylinder machine containing a fluid system has a stirring device in the cylinder. The piston is frictionless and it is held down against the fluid due to the atmospheric pressure of 101.325 kilopascal. That means the atmospheric pressure is enough to balance the fluid and the piston. So the pressure exerted by the fluid is exactly same that to the atmospheric pressure. Okay, so both the piston and the fluid are maintained in a thermodynamic equilibrium condition. Now what happens? The stirring device is turned 10,000 revolutions with an average torque against a fluid of 1.275 meganewton. Meanwhile, the piston of 0.6 meter diameter moves out 0.8 meter. Now how does it happen? The stirring device obviously stirs the fluid. As the stirring device starts to stir the fluid, there is a increase in the temperature. Thermal energy is generated which helps the fluid to expand. Since the fluid is trying to expand itself, it obviously pressurizes the piston and the piston obviously moves in the upward direction. Here the uh, distance in which the piston moves is given as 0.8 meter. Now we need to calculate net work for the system. Now this is a very important problem. Now you need to calculate the net work transfer for the system. Now if we consider the fluid system is receiving work. That means the surrounding is doing work on the fluid system. What is the surrounding here? The stirring device. So stirring device is working on the fluid system, and consequently the fluid system is doing work on the piston. So the work done by the stirring device will be considered a negative work for the fluid system, because for the fluid system the stirring device is the surrounding and the surrounding is doing work on the fluid system. So obviously that has to be treated as negative work, whereas when the fluid is doing work on the piston, this should be treated as positive work. So let us find out what is the work done by the stirring device. So once again I am saying the work done by the stirring device for the fluid system will be considered negative. So better to write work done by the stirring device on the fluid system and work done by the fluid system on the piston. So let us just write down all the information available here, and then we shall proceed on to the problem. Okay. So let us calculate the work done on the stirring, work done by the stirring device on the fluid system. So we consider that work as Ws. Now the formula was T into theta, if you remember. So here we need to express that theta in terms of revolutions, the RPMs. So we shall write 2 pi n into t. Okay, so n is given as 10,000, t is 1.275 meganewtons, and ultimately you will find the result will be 80 kilojoule. Okay, so the result will be 80 kilojoules. Now you need to calculate the work done by the fluid on the we need to calculate the work done by the fluid system on the piston. Now that will be calculated as WA. So it is force into displacement. Now what is the force here? It is pressure times area. This is very simple. And the displacement here refers to the piston which moves out by 0.8 meter. So the displacement considered here will be 0.8. So WA, the pressure is already given to you as 101.325 kilopascal. Area, you know the formula, pi by 4 d square. The diameter is given to you as 0.6 meter. So ultimately, if we calculate this uh, values, then we will find 22.9 kilojoule. Now, as I have told you earlier, this WS should be considered negative because this is the surroundings which is doing work upon the fluid system, and here the fluid system is doing work on the atmosphere. So the total work transfer for the, let us W be the total work transfer for the system. So it will be WS plus WA. So the values will be minus 80 plus 22.9. So the ultimately we will get a result of minus 57.1 kilojoule. So the concept was only to find which work is positive and which of the work done is negative. Okay, you just need to identify the surroundings and the system. So if you are able to understand which one of the interacting systems are surrounding, then you can identify the work done is positive or the work done is negative. This is very simple, but you just need to concentrate on the problem. You just need to read the problem very minutely so that you can understand the problem, you can understand the concept of surroundings and system. Lot of students I find that they don't understand the concept of surroundings and system. So it is always written in the problem, it is always mentioned in the problem. You just need to clearly read out that. So if you are able to clearly read out the problem, then it is very easy to identify. It is very easy to identify. Now we'll stop this discussion on parallel work here, and we shall move on to a new topic which we call as flow work. So flow work is basically important for open system. Now we shall just see what do we mean by flow work and how does it. So let us start our discussion on flow work. Flow work uh, becomes important or significant in the case of open flow devices or open system. Now, from the discussions of the first lecture, we know that open system means a system where both mass and energy transfer is allowed. Now, let us consider this. The dotted lines here refer the boundary. So we have taken a certain diagram for an open flow device, and these dotted lines in the yellow color refers to the boundary. This boundary is always called as control surface, and the fluid which is contained inside this boundary is defined as the control volume. So now we can say much more specifically that a certain amount of fluid is trying to enter a control volume. So what will be the work done needed by this fluid to take entry into the control volume? So to find that, to analyze that portion, we have imagined a piston cylinder arrangement. Okay, and some amount of fluid is contained within that piston cylinder arrangement. Okay, so here you can see that this is the piston cylinder arrangement. The piston has an area of A. It is exerting an force F on the fluid, and the fluid is also exerting a force by the virtue of the pressure P. So at equilibrium condition, the pressure exerted by the fluid is equal to the force exerted by the piston. So you can write F is equal to P dot A. Okay, now we need to find out the flow work. Okay, so please hear very carefully. Flow work is almost same, or it is analogous to displacement work. So that means flow work and displacement work are conceptually very much same. Okay, so if this piston is displaced by a small amount of um, length, say dl, then the work done will be obviously P into A into dl. So this is similar to the description um, in the first lecture, sorry, in the calculation of displacement work. So the work done will be dw, or simply w we can also write. So dw is equal to p dv. So pdv is the pressure. Okay, so at inlet condition, the surrounding is doing work on this system. If we consider the control volume as our system, then the surroundings is doing work on this system. So at inlet condition, if we take uh, P1 V1 as the inlet condition and P2 V2 as the outlet condition, then we can say the at inlet condition it will be minus P1 V1 d M1. Okay, so the work done at inlet condition it will be P1 V1 d M1. Okay, okay, you must be wondering from where this M come. Okay, sorry, I'm very sorry. This will be P small small v dm. Okay, this v, the small v refers to the specific volume. Okay, the small v refers to the specific volume, and m is the mass flow rate. Okay, I think you have understood now. M is the mass flow rate by which the fluid enters the control volume, and V is the specific volume. So at inlet condition, let us write down W1. It will be minus because the surroundings is doing work on the control volume. So it will be minus. And at the outlet condition, it will be plus. Okay. The system is exerting some amount of force on the surroundings, so it will be plus P2 V2 Tm. So this information will be very much required for you when we'll be discussing about the first law, when it will be applied to the flow process. So this information you must remember. So at the inlet condition, the surroundings is applying force to take entry into the control volume. That means the surrounding is doing work on the control volume. Whereas when it is moving out of the control volume at the outlet condition, the work is done on the surroundings by the system. Okay, I hope you have understood the concept of displacement work. Now I believe the concept of work transfer in a whole has been discussed to you, and we shall stop on work transfer. In the next class, we shall take problems on different kinds of work transfer. They will be conjugated problem. That means we'll be discussing the problem based on work and heat transfer conjugately. So to solve that kind of problems, we need to understand what is heat transfer. Okay, so let us stop the discussion on flow work here, and just let us move to the discussions on heat transfer. So let us see what do we mean by heat transfer and how it affects the thermodynamics perspective. So let us start our discussion on heat transfer. So we have already mentioned that mm, energy in thermodynamics can be understood from two different perspectives: energy in transit and energy in storage. So, energy in transit refers to heat transfer and work transfer. So, we had discussed about this work transfer much more in a very uh, deep way, in a describing manner. Now, we shall move on to the discussions regarding heat transfer. So before starting the discussions on heat transfer, we need to know what is heat. So heat is nothing but a kind of energy which is transferred across a boundary because of the temperature difference. So whenever there is some kind of temperature difference between system or surroundings or between two interacting system, heat will start to flow from the high temperature to the low temperature. Now there are different modes of heat transfer. Primarily, you can say that heat transfer takes place through the modes of conduction and radiation. Now, what are the basic terminologies which we need to understand for heat transfer? What are the basic sign conventions? So, in case of heat flow, when heat is flowing from the surroundings to the system, that means heat flow into the system is always taken as positive. So heat into the system, that means this Q1 is obviously positive because heat is entering the system. So there is heat flow into the system, whereas whereas this Q2 will be negative. Okay, because heat is releasing out from the system. So I hope you have understood the concept of heat transfer and the basic sign conventions of heat transfer. Okay, so you must remember heat is not not an energy which will inevitably cause a temperature rise. Okay, if you consider the case of latent heat, then the temperature always remains mm, constant. Okay, the temperature and pressure always remains constant in case of the phase change. So whenever the phase change process is occurring, it means that uh, though heat is transferred, though some amount of heat is transferred, still it doesn't manifest in the increase of temperature. Okay, but and conversely, you also remember whenever there is a temperature rise, that doesn't necessarily mean that the reason is heat. Okay, so so you have to understand that when a temperature rise in a system occurs, it may not be because of heat transfer. Some internal process may go on that is helping the temperature to rise. Okay, and obviously the temperature can be increased through the work transfer process also. Now, a process in which no heat crosses the boundary is called as adiabatic process. Uh, we had a discussion regarding this adiabatic process in the previous lecture in a much detailed manner, so I will not get into that. And a wall which is impermeable to the flow of heat is an adiabatic wall, whereas a wall which permits the flow of heat is a diathermic wall. So just like work transfer, heat transfer is also a path function. So the amount of heat which is being transferred when the system changes is its state from point 1 to point 2, the amount of heat transfer always depends on the path, not it doesn't depend on the states. Okay, so you know that 1 to 2 dq cannot be written as, it cannot be written as q2 minus q1, because this is a path function. So what we have to write, we have to just write, we can write q1 to 2. So since it is an property, it is a property which depends on the path, we need to know the specific uh, like work transfer, heat transfer is also a path function. Okay, so depending on the paths, the heat transfer needs to be calculated. So if you find a quasi-static path, then the area under that path will depend on the amount of heat which is being transferred. So whenever you will see a system changes its state from 1 to 2 following a quasi-static equilibrium process, then the area under this curve will give you the relevant information about heat transfer. Now the coordinates to express heat transfer will be T and S. T is an intensive property. So here this X is referred to an property which is unknown to us. Okay, actually uh, in the later on you will understand this X is nothing but S. S is the entropy. We shall discuss on this entropy on the later lectures, but this X is considered to be an extensive extensive property, whereas this T or this temperature is considered to be an intensive property. So uh, the area under the quasi-static path denotes the heat transfer. So area under TS curve always denotes the heat transfer, and the area under PV curve denotes the work transfer. So these two information you should remember for your lifetime, because this will help you in many different ways. Okay, so we can write dq. So this uh, uh, line, this cut, d cut q is equal to t dx. This means that this cut suggests that this is an improper or inexact differential. Okay, so we can write dx dx is equal to 1 by t dq, d cut q. Okay, so this 1 by t is nothing but the integrating factor. So if you have the concepts of differential equation, if you remember the concepts of differential equation, you know how does an integrating factor act. So this 1 by t is nothing but the integrating factor here. So and this dq is an inexact differential. So I hope you have understood the concepts of heat transfer, and uh, we will end this lecture session here. In the next class, we'll take some conjugated problems of work and heat transfer, where we will see that both uh, the system is transferring both heat and work. So at that moment, how do we need to calculate? How does the problem change? How does the problem evolve? From that point of view, we need to understand that. So thank you. Let us end our lecture here. Thank you for being